This tutorial is 7.8, geometric probability using area. There were other geometric probability problems inside section 7.8, but I wanted to do the area ones mainly because it reinforces many of the topics that we've already done in this chapter. The idea of probability is, well, let's look at this circle. I've got a circle, and half of it is dark and or kind of brownish, and half of it is white. And let's say I just randomly pick points on the circle. Everywhere around here, just randomly picking points. And the idea is, what's the possibility that any point chosen at random would fall inside the shaded area? Well, clearly it looks like the shaded area is half of the circle, and so if I'm doing this correctly, my probability should be 1/2. Well, the probability of an event is defined as the area of the favorable region divided by the area of the entire region. Well, if I'm trying to find the probability that the area would fall inside this shaded region, that is my favorable region, is the shaded part. What is the area of the shaded part? Well, it's half a circle. The area of a circle is pi r squared, so the area of the favorable region is 1/2 pi r squared. I'm going to divide that by the area of the entire region. The entire region is a circle, so its area is pi r squared. I can cancel out the pi r squareds, and sure enough, the probability that a point chosen at random inside that circle will be in the shaded area is 1/2. For all of these, we're going to take the area of the shaded region, or the area that we want to know, divide that by the area of the entire region that it's possible to get a point from, and that will be our probability. Let's look at a few examples. In this example, I have a circle with radius 2. This circle with radius 2 is lying inside a square with a side length of 6. And I want to know, if I choose a point randomly that I know is inside the square, what is the probability that its area is going to be within the circle? What's the area of my favorable region? Well, that is the area of a of a circle with radius 2. The area of a circle is pi r squared, and in this particular case, r is 2. The area of a circle with radius 2 is 4 pi. What's the area of the square? Well, the area of a square is a side squared. 6 times 6 is going to be 36. And so the probability that I would pick a point inside the circle, that shaded circle, 2 by 2, is going to be 4 pi over 36, which I can simplify to pi over 9. Now, it also asked us to give this probability as percent. Looks like it's a little bit less than half, so a little bit less than 50%. Let's give it a shot. I guess I better get a calculator. And I'm just going to do pi divided by 9. Apparently, it's going to be approximately 34.9%. So the probability written as an exact number, pi over 9, what is that as a percent? You got about a 34.9% chance of lying within the circle if you pick any point within the square. Okay, look at this one. I've got almost looks like a little flower, and I'm going to take a point chosen at random on the figure. The figure I'm talking about here is this whole flower looking figure. And I want to know, if I choose a point, I'm calling everything inside the square orange, I'm calling everything outside the square yellow. What's the probability that any point chosen at random would lie within the yellow region? What's the area of the yellow region? I don't have any numbers for the radius, but it sure looks like I've got 4 half circles. 4 half circles is the same as 2 circles. The area of one circle is pi r squared, so the area of 2 circles is 2 pi r squared. That's my favorable region. That's the region that I want to be able to draw something from. If this is a radius going from here to here, my square must have a side length of 2r. So a square has a side length 2r here, 2r here. 2r times 2r is 4r squared. The area of my square is 4r squared. What's the area of the total figure? Well, it's those two circles plus the area of the square. So my total area is 2 pi r squared plus 4r squared. Make sure that makes sense for you. All right, let me do a little work here. That's going to be equal to r squared times 2 pi, correct, on the top. On the bottom, I can also factor out an r squared, and I will be left with 2 pi plus 4. I can cancel out the r squared. My exact answer for the probability is going to be 2 pi over 2 pi plus 4. All right, example 3. I've got a square inscribed inside a circle. What's the probability that the point chosen at random inside the circle will also be within the square? In this case, my favorable region is the square. I'm going to run a radius here. Everything's based upon this radius since I'm not given any numbers whatsoever. And I want to know if I have a radius of r, what is the area of my square? Well, we've done this quite a few times. Remember that if I've got a radius of r, I have a diagonal of 2r, and now I have a 45, 45, 90 triangle with a hypotenuse of 2r. That means that my length of my side must be 2r divided by the square root of 2. Multiplying the top and the bottom by the square root of 2, I get 2r root 2 divided by 2, which is r times the square root of 2. Remember, we can cut this number in half, put a square root of 2 outside. The length of one side is r times the square root of 2. The length of the other side is r times the square root of 2. So the area of the square is r times the square root of 2 squared, which is 2r squared. So the area of my favorable region is 2r squared. What is the area of the circle? Well, the area of a circle is pi r squared. So the probability that I would be within the square is going to be 2 over pi, 2 over 3.14-ish. Example 4. I have a circle inscribed in an equilateral triangle. What's the probability that the point chosen at random inside the triangle will also be within the circle? To me, this one runs a little bit trickier. Let's see what we can do. Once again, since I'm given no information about units at all, I'm going to just start off here with a radius. When I start off with a radius, I'm also going to draw the radius of the equilateral triangle. I've got a radius of a circle. I've got a radius of an equilateral triangle. This radius of the equilateral triangle took this 60-degree angle and cut this piece into 30. And now I have a 30, 60, 90 triangle. Because I have a 30, 60, 90 triangle, I know the short leg is r. That means that the longer leg, this longer leg here, must be that number r times the square root of 3. So the length of the entire side must be twice of that. The length of the side of an equilateral triangle, in this case, is 2r times the square root of 3. Now, fortunately, we have a formula for the area of an equilateral triangle. The area of an equilateral triangle is s squared root 3. Let me try that again where you can actually read an s. S squared root 3 divided by 4. So in this case, it's 2r times the square root of 3 squared times the square root of 3 divided by 4. Well, 2r times the square root of 3 squared is going to be 2 times 2 times 3, which is 12r squared times the square root of 3 divided by 4, which 12 and 4 goes into 4 one time, 4 goes into 12 three times, and I end up with 3r squared times the square root of 3. Now, that was not my favorable region, that's my total region, the region of the equilateral triangle. So my total region is 3r squared times the square root of 3. What's the area of my favorable region? The area of my favorable region is the area of the circle, pi r squared. Well, now the r squares are going to cancel out, and my probability that I would lie within the circle, if the circle is inscribed in an equilateral triangle, is pi over 3 times the square root of 3. It's all a matter of being able to determine the area of the two figures and then being able to cancel out terms as we go along. The only thing I can do to make this better for you is let you try some on your own. So go ahead and pause the video and try problem 1. This problem hopefully wasn't too hard. I've got a circle, I've got an arc here that has 50 degrees. So the arc of this shaded region must be 310 degrees, since the whole circle totals up to 360 degrees. Okay. So what is the area of the favorable region? It's 310 over 360 times pi r squared. And the area of the whole region is pi r squared. All I'm really going to be left with is 310 out of 360 degrees, the measure of this arc here divided by the whole circle, and I will end up with a probability of it being in the shaded region of 31 over 36. Let's do something a little tougher. Find the probability the point chosen at random inside the square will be inside one of these 4 circles. Just like before, I don't have any units. I'm going to call this R. What's the area of my favorable region? Well, I've got 4 of these circles with radius r, so my favorable region is 4 pi r squareds. What's the area of the entire square? Well, if this is r, then this is r, and this is r, and this is r. My side length is 4r. My other side length is 4r. The area of the square, therefore, must be 16r squared. The r squareds will cancel out. 4 goes into 4 one time, 4 goes into 16 4 times, and the probability that I will lie within one of these circles, if I lie within the square, must be pi over 4. How about problem 3? Don't let this one fool you. This is like a circle that got cut in half and moved around the other way. But in the end, my favorable region is just a circle whose radius is r. So the area of my favorable region is going to be pi r squared. Kind of just like before, what's the length of the side? Well, if this is r, the length of the side must be 2r. Because I'm giving you squares, making it nice on us, the area of the square is 2r times 2r, which is 4r squared. Like before, the r squareds cancel out, and my possibility for being inside the shaded region, if I'm inside the square, is going to be pi over 4. That's an equal sign. One more. Let's go ahead and pause your video and try problem 4. In order to solve problem 4, I need to know the area of the segment. Remember that the area of the segment is going to be equal to the area of the sector minus the area of the triangle. That may not be the best mathematical notation up there, but it's what I'm going to use. The area of the segment is the area of the sector minus the area of the triangle. How do we find the area of a sector? We take the number of degrees in its central angle, 120, divided by the degrees of the whole circle, which is 360, times the area of the whole circle, which in this case I don't know what it is. With a radius r, it will be pi r squared. So the area of the sector must be pi r squared over 3. That gives me the area of the sector. Now, what's the area of the triangle? Well, in order to find the area of the triangle, I am going to draw a perpendicular. I cut that 120-degree angle in half. That's going to make this angle 60 degrees, which makes this angle be 30 degrees. And remember, this is my radius. The radius now is my hypotenuse. If the radius is my hypotenuse and the altitude drawn here is the short leg, then the altitude must be r over 2. And if the altitude is r over 2, then this piece down here must be r over 2 times the square root of 3. So far, so good. I have an r over 2 times the square root of 3 plus another r over 2 times the square root of 3. That gives me 2 r over 2's times the square root of 3, which means the whole part, this whole base, is r times the square root of 3. The formula for the area of my triangle is going to be 1/2 the base, r times the square root of 3. Hey, look at that. I got right back to this piece right here, times the height, which is r over 2. And so when I get through working this out, my area must be r squared times the square root of 3 over 4. I'm going to multiply. So there's my favorable region. My region of the whole circle, therefore, is, and clearly I'm going to have to finish this one later. In fact, finish it on your own, and we'll do it in class.